Hello. So we continue our discussion about the current mirror. This is the building block that we discussed in our previous module. And here was that circuit where we applied the voltage source, VCC, and then there was this resistor R that drew the current I reference. We call it as an input current. That current is being flown into the transistor Q1, and that is the collector current. Then it is splitted into two equal parts, that is IB1 and IB2. And we said the collector and the base of the Q1 are shorted together, making this as a diode connected transistor. So diode connector transistor has such characteristics. It has the input current versus an input voltage, and that's for the values of VCE. You have the exponential behavior between voltage and the current. And this makes sure that VBE1 was equal to VCE1. And we see that because the transistors are exactly matched, that is Q1 equal to Q2 in all the properties. And also we say that they are of equal size at the same temperature. Therefore, their VBs are also equal, that is VB1 drop and VB2 drop. So it is equal to VBE2. And therefore, we see that the voltage here at the collector of the second transistor and the voltage here at the base of the second transistor. So the voltage at the collector base, that is VCB of the transistor Q2 has to be VCB has to be greater than or equal to 0. So for a minimum voltage across the collector and emitter of the transistor, you have this I out that is a replica of your reference current. Okay, and this is that V out, which is minimum voltage required to keep the transistor active so that you have a constant current delivered to the load. So that's the minimum voltage, which is the V out right here. Now, there is a concept of sink and the source. So, for example, if you are given a current source at the input side of your current mirror, then it looks like the circuit looks like a virtual short, and it reflects, swaps the direction of flow also, this current into the output side to produce a current sink. So when you see such arrangement, it is called as current sink. On the other hand, if you are given a current sink, you see the current is getting synced here at the input side of it, then the current mirror acts as a virtual short, reflecting this current at the output side, and therefore we obtain a current source. So here we obtained current source. Here, look at the direction, we obtained the current sink. So that's the principle of it. There are now few facts. One of the fact is we just saw this one, and now we see other facts of the transistor. So current mirror are known for its relatively high output resistance, which helps to keep the output current constant regardless of the load conditions. It means when you have this I out, which is a replica of your reference current, the output transistor current can be drawn like this, ideally. So this is the minimum voltage that is required, which is, we have seen that this is the V out right here. So this is the minimum voltage that must be dropped across the collector emitter of your transistor Q2 so that your transistor is maintained in an active region. When I say an active region, it means the transistor is operating in a saturated mode. So if the current is constant with respect to voltages, as you can see, so the slope of this line, slope is equal to 0. So the output resistance, which is output resistance of the transistor Q2, is actually infinity, right? So output resistance is basically 1 over the slope of the transistor. So you have just a minute. I made a mistake or what? Yeah, so we'll say like that. So you have this output resistance infinite. So when you have an infinite resistance, you can say that it acts as an ideal current source. Like in the previous slide, we saw uh, here, you are basically getting the current source, right? From the input side is the current source, and you have a current sink at the output. But this circuit, your input side is your current sink, and what you produce is a output current source, right? You get a output current source. So now in our circuit right over here, you basically having the current sink, and you are basically then having the current source. You are producing at the output the current source, and the output resistance is infinite ideally. However, in practice, you are going to have the finite resistance. It means your current will be somewhat like this. So it will increase when you increase the voltage across it. So that then RO is finite. It will be still very high, but still it will have a finite value. And this is due to the due to the what you called early effect of the BJT. That effect plays a role in having the finite output resistance of the transistor. Now at the input side, when you look at the input side of the transistor, there you have Rin very low, okay, relatively low input resistance. So which helps to keep the input current constant regardless of the drive conditions. Okay, so your I reference will always have the constant value regardless of your drive conditions. Third point that we can have a look at when we discuss the facts about current mirror, it is used to provide the bias currents and active loads in amplifier stages. So for example, in this circuit, you have this transistor, you want to have a current flowing through this transistor. So this is the current source that is working out for this. In another word, you want the active loads in amplifiers. For example, you have the differential amplifier as a transistor. For example, this is how your transistors are. So these are your input transistor, let's say Q1 and Q2. And then you have, let's say, emitter resistance Re, and then you apply input V1, and then here you have input V2, and usually you connect the resistors in the, this is your VCC. So this resistor RC1 and RC2 acts as a load, but current mirrors can be used in as an active load. So instead of resistor, you replace them with these transistors as a current mirror. Okay, so you can see now you basically have this I reference that is coming from VCC, and the resistor RC1 will be replaced by this Q1, resistor RC2 will be replaced by Q2. So in both the branches, here you will have the currents that is flowing into your transistor. The fourth point that we would like to state here is about the ideal current mirror is simply an ideal current amplifier with a gain of -1. So we know that the ratio of I out divided by I reference, or which is I in, is equal to 1. So that's why we say that it's a current mirror, because I out is equal to I reference. But if I out has the same magnitude but opposite polarity, so you can sometimes have a negative sign here. That's why we say it's simply a current amplifier with a gain of -1. You can also have, when you say it is a current amplifier, you can design it in a previous model we've seen for a particular number of gains, for example, -3. So I out will be 3 times the input current, and it will be having the negative sign, which is the opposite polarity, equal magnitude in case of gain equal to 1, but in case of gain equal to 3, it has a 3 times larger magnitude than the input current. Now, there is another limitation that you see here, that is your ideally we say that the I out should be exactly equal to I in. So your I out is equal to I in, as we can say that here. So there are symmetrical errors, systematic errors, and some random factors that makes this not the case. For example, some disturbances, noise, temperature variations, mismatches in the transistor properties, etc. So this is not going to be the case in your practical situation. Okay, so I out is equal to I in. This is ideal condition. I out is not equal to I in. This is your practical condition. As a designer, your job is to meet the ideal condition as much as possible. So, for example, I just explained in the previous slide, there is a concept of incremental output resistance. It determines how much output current varies with the voltage seen at the mirror output. So this is the voltage that must be maintained across the BJT transistor Q2 to keep the transistor active. It means in the saturation region. And when we say a saturation region, you make sure that your emitter junction, base emitter junction is forward bias, and this junction is also forward bias, right? Right here. So if it is not forward bias, this is also forward bias. So if the collector base junction or base collector junction is not forward bias, then your transistor comes out of the saturation. It may enter in the linear region. So how we'll see that in the graph. So here is your graph. Here is the IC2, which is your I out, and this is your V out, that is basically also VCE2, right? VCE2. And we say that this is how your transistor is going to behave. So ideally, your current should be like this, and this is the actually this is the V out, right? This is the minimum voltage, V out minimum, and this is actually your VCE, that is the voltage. And this slope of this curve determines you have incremental output resistance, and slope of this is the ideal, as I explained previously. RO is infinite. Okay. Now there is a one more point, the minimum voltage drop across the output leg of the mirror necessary to maintain the desired output current. So what I just explained through this curve. And then there is a concern about temperature stability and the frequency also of the current mirror. Now we talk about the all these limitations one by one. So due to mismatch of the transistor, for example, and some temperature variation and some disturbances, the first limitation is about gain. So there is, we expect that I out is exactly equal to I in an ideal case, but this is not going to be the case for practical reasons. And first reason is the gain one. Let's expound on that. So the output current, rather, we would say, is somewhat smaller than the input current, I reference. So not, yeah, it is smaller than the I reference. Why? Because you see, the I reference is coming here, and then it is the collector current of the transistor 1, and then the same current goes here and becomes the two currents of the transistor IB1 and the IB2. So I reference is the sum of IC, which is this one, plus IB1 plus IB2. So therefore IC, which is going to be uh, uh, IC, uh, which is reflected here as I out, we would say IC, which is equal to I out, would be I reference minus 2 times IB. So IB1 plus IB2, assuming IB1 is equal to IB2. So here your output current of the transistor Q2 IC would be input current minus 2IB. So this factor is less. In case of a MOSFET transistor, there is no concept of base current. So gate is insulated. Therefore, you can expect that, okay, I reference will be IC or I out, that is the drain current, will be exactly equal to your reference current in the case of MOS transistors. Okay, so that's why I said here the significant advantage of MOS current mirror that we will see in future models is the lack of base current induced error. So because of the base current in the BJT base current mirror, you have some error. Okay, now moving to the next part, we see here there next limitation is due to the compliance voltage. As I said, there must be a minimum voltage, which is V out, that you, or you can say that VCE minimum across transistor Q2 to keep it in the biased in the active region. So if the collector voltage keeps following, and the base voltage is constant, right? So this junction may come out of the forward bias, and it may become reverse bias, right? So here is your N, this is your P and N. So if the voltage at the N is the positive voltage, it may become negative. So this, just a minute right here, let me explain. Right, so you have to make sure that the collector base junction of the transistor Q2 is forward biased, and for that you have to maintain the minimum voltage across it, so that to keep the transistor active, your voltage should be equal to 0, collector to base, or greater than 0 volt, right? And that means your lowest voltage can be equated or given by this equation to have a correct current mirror behavior, and which is equal to this equation, Vt logarithmic ratio of collector current divided by saturation current plus 1, where Vt is your thermal voltage. So theoretically, you can calculate your VCV, which is called as compliance voltage with this equation, right? So here we see that the lowest output voltage that will result in correct mirror behavior, which is called as compliance voltage, is V out, which is VCV, should be VBE. under biasing condition. Okay, so when you have a VBE across collector emitter, you basically have VBE is equal to VCE. And therefore, the VCB is equal to 0. Okay, and this will maintain the output transistor at the output level, current level IC, and VCB will be 0. Now, there is more explanation about the output resistance. So here you see the limitation for the transistor. VCB is equal to 0 volt, because here is the collector, here is the base, and we have shorted that. That's why this is 0. Now, if the VBC is greater than 0, so voltage at the base of the transistor 2 and the voltage at the collector, if this difference, that is VBC or VB minus VC, is greater than 0 in transistor Q2, we would say that collector current in transistor Q2 will be somewhat larger than uh, the current in Q1 due to the early effect. So this is what we would see, that this is how the current in transistor Q2 will vary. Okay. And IC2 will be greater than IC1. Okay, somewhat larger. So in other words, the mirror has a finite output resistance. As you expect, it should be a constant, but it is varying. And this value theoretically can be equated to this equation, which is VA plus VCE divided by IC. So VA is the early voltage, VC is the voltage across the transistor's collector emitter divided by the DC value of the collector current. So that's all for your module, this module, and we will continue our discussion with the remaining modules. Stay tuned for the more content that will keep adding on the channel. Now in upcoming module, we are going to design this current mirror circuit and simulate its behavior.